Okay, the last one. Here we go. These should hopefully actually be fairly quick. So, number 14, let me turn that off. You've got 2x to the fourth plus 3x to the third. You want to say, when is that less than 2 minus 3x? Now, inequalities, all of a sudden, the nice thing is we handle inequalities almost exactly the same way as we handle equations. The big guideline for inequalities is make sure you're never multiplying or dividing by -1 without flipping the inequality. Whenever you multiply or divide an inequality by -1 on both sides, you have to reverse the direction of the inequality. That's because as you talk about a very, very large number, if you put in a negative, that changes what we think about in terms of big numbers and small numbers. A million is a big number, but -1 million is a very, very small number. So negatives do change our ideas of bigness and smallness, to be all technical. So we're going to solve this the way we normally would. Just kind of be careful of that and keep in mind how we handle inequalities. So if this was an equation, the first thing you would likely do is set it equal to 0. So we're going to do that. We're going to take that and set it, well, less than, in this case, 0. Now the nice thing is this equation here, or the expression on this side, should stand out as being fairly familiar. It's the same one that we've been messing with for a while on this exam. And again, I did that mostly for expedience. But this is something we know how to graph. We've already found, if you graphed that object, we've already found its x-intercepts because you found its roots earlier. They were -2 and 1/2. So technically 0, 1/2, and 0, -2. We know its y-intercept. The y-intercept is just the constant, so the y-intercept is -2, 0. And we know the other two x-intercepts are complex, so it doesn't have any other x-intercepts. It's a fourth degree polynomial, so we know its end behavior. It has to be going up and up. That was one of the first things we did in chapter 4. So if we want to get a quick sketch of this, it has to go through 1/2, has to go through -2, has to go through that -2. And we know it has an extra wiggle in it somewhere, but we don't really know where that extra wiggle is. It could be up here, could be down there. I think if you graph this on your calculator, it's down in there somewhere. But we know that's what it has to look like because we know its x-intercepts. We found them. We know the other two are complex, which means there's a wiggle in there somewhere that's not wiggling hard enough to cross an axis. We know it goes down here. We know it opens upward. We know they head in the same direction because it's a fourth degree polynomial. There's a tremendous amount of things that we know because of this section. The key is often just making sure that we know it. There's a big difference between having been exposed to these tools and internalizing these tools enough so that when you look at this expression, all of these things occur to you. This is upward facing, so it's going to kind of be parabolic-like, but it's going to wiggle a couple times. We can find x-intercepts using our rational root theorem, so find those. The other two are complex, so that means we're going to have some wiggles that aren't causing other x-intercepts. Great, we might have to go find those later. And in calculus, I'll show you a tool to even find those if you want to. X-intercepts, we know where that is, so we know it doesn't cross. None of these have multiplicities, so it's not hitting and bouncing. So a whole bunch of information in this section that is really easy to just have be this muddle, but you really need to organize it into useful information. So for a problem like this, we're asked, when is this, the values of this expression, when are they less than 0? Well, the values of this expression are the outputs, the y values. The y values are less than 0 for all these points down here. All those points have negative outputs. What are the x's that make these outputs less than 0? All x's from -2 to 1/2. All of those x values make this into a negative number. We know it's a negative number because it's below the graph. So our solution set is x, where x is got to be less than 1/2 and greater than -2. That's in set builder notation. Or in interval notation if you want, going from -2 to 1/2. Make sure to use the parentheses because at -2 and at 1/2 it's equal 0, not less than. So that's it. And at this stage, I don't really care whether you answer it in set builder or in interval notation, either way as far as I'm concerned, but I do want to make sure you can read both. So really this, part of this is easy because, it's so quick, because we already knew those, but you know how to find these if you don't. This is a large polynomial. You want to find where its intercepts are, where its roots are, where it's actually equal to 0. That's what our rational root theorem and our synthetic division and all those tools are for. So you want to make sure that those tools are coming to the forefront when they're needed. Okay, big lecture, I know. So, number 15. You got to have some sympathy for me. I don't get to lecture at you every day, so when I have the chance to get on my soapbox, I got to do it. Okay, now a dangerous problem down here. We're trying to solve that inequality. Now, if this was an equation, you would quite rightly want to multiply both sides by x minus 4. And that's very good if it's an equation. It's very dangerous if it's not. Because this isn't an equation, we can't multiply both sides by x minus 4. And I'll tell you why. I better tell you why, huh? We said up here, the big thing about inequalities is if you multiply or divide by a negative number, you have to reverse the direction of the inequality. Okay, so if we multiply both sides by x minus 4, is x minus 4 positive or is x minus 4 negative? I'm pausing to give you a chance to think about that. So what do you think? Is x minus 4 positive or is x minus 4 negative? If you're thinking, well, that depends on x, you're right. Sometimes x minus 4 is positive, which would mean if we multiplied by both sides by x minus 4, we should leave the inequality symbol alone. But sometimes x minus 4 is negative, in which case we should reverse it. Sometimes x minus 4 is equal to 0, okay, when x is 4, but we can't multiply both sides by 0. It's not allowed. So multiplying both sides by something that we don't know to either be positive or negative, not only do we not know whether we should switch the inequality or not, but since it can be both positive sometimes and negative sometimes, depending on what the x value is, we'd have to essentially both flip and not flip the inequality. And we can't do that. So because of all that, never multiply both sides of an expression by both sides of an inequality by a variable expression that can take on both positive and negative values. Now, if this was x squared plus 1, okay, x squared plus 1 is always positive for any x, as long as it's real, so you could multiply by it safely. But this can take on both positive and negative values, so we can't. But we still want to be able to solve this. So just like up here, we essentially want to set it to 0. When you can't isolate purely, set things to 0. How do we set it to 0? Well, we need this to be 0, we need this side to be 0, so subtract 5 from both sides. Minus 5 is less than or equal to 0. Now that looks a little ugly. You might be thinking, what? Do we have to get common denominators? Yes, you have to get common denominators. We have to perform that subtraction. To perform that subtraction, we need good old-fashioned common denominators. So 3 plus x over x minus 4 minus 5 times x minus 4 over x minus 4. It has to be done, people. Okay, but the nice thing is, from there, we can hopefully progress nicely. So we've got 3 plus x minus 5 times x minus 4 over x minus 4 less than or equal to 0. Simplify this numerator. I need another piece of paper here in a second. So how about 3 plus x minus 5x plus 20 when we distribute that negative 5 over x minus 4 is less than or equal to 0. It's a 0. So what? How about negative 4x plus 23? That's just ugly. Over x minus 4. Where is that less than or equal to 0? Okay, so it's not the most aesthetically pleasing rational function ever to exist, but it's still a rational function. So we can do the same thing we did over here. Graph it. Here we wanted less than 0, so we're looking for the below part. If we want greater than 0, we'd look for the above part. Here we're asked, where is it less than or equal to 0? So if we had this graph, we could do the same thing. So graph this. Again, it has x-intercepts where the numerator is 0. Negative 4x plus 23, where is that equal to 0? That's equal to 0 at, what, negative 4x equals negative 23, so x equals 23 fourths. 23 fourths is almost 6. So 1, 2, 3, 4, 5, 6. So x-intercept right there. It's got a y-intercept at, let that be 0, let that be 0, negative 23 fourths. So 1, 2, 3, 4, 5, 6. Oops, that's 5, that's 6. So again, almost negative 6 now. It's got a vertical asymptote. Where's that vertical asymptote? Where the denominator is 0, so x minus 4 equals 0 at x equals 4. So it's got a vertical asymptote at x equals 4. That's good. And we look to see if it has a horizontal asymptote. The degrees match, so the horizontal asymptote happens at the ratio of the lead coefficients, negative 4 over 1, or y equals negative 4. A lot of symmetry in this problem. So you've got one sweep down here, another sweep up there. So that's a fast version of what we did on those numbers 9 through 13, I think it was. So we're asked, where are these values less than or equal to 0? Well, those values are less than or equal to 0. What x values make it less than or equal to 0? Well, lots. All of these, all of these, all of these. Not x equals 4. We're undefined at x equals 4. And then all of those up to that point. Nope, 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 not those, sorry. Not those. But from these on. So all of these are making negative values. All of these are making negative values. So really everything except this little gap right in here. So if we want to express a solution set, well, we're certainly going to go from negative infinity all the way to where this asymptote is. So from negative infinity all the way up to 4, but not including 4, because at 4 we're undefined. And then unioned with this point there, which we found, that was the x-intercept, 23 fourths. And at 23 fourths, we are equal to 0, and we can be equal to 0, so hard bracket. And then all the way out further than that, you're always down here negative, so all the way out to infinity. So a nice big interval notation solution for where is that less than or equal to 0. And again, if we'd been asked where are we greater than 0, it would just be this little spot here. Where are we greater than 0? Well, everything in there. So being able to draw those graphs are very handy ways to solve these types of inequalities. Okay, that's the last one. Gotta go. Best of luck to you.